We were looking at the bootstrap, and it's a specific case where, excuse me, we have two investment opportunities, these two assets with an associated random variable giving us the return on each asset. And that's return X and return Y. And our question is, how much of our capital are we going to invest in X as opposed to Y? We'll assign alpha to X and 1 minus alpha to Y for the simple reason that these two proportions should, of course, add up to 100%, assuming that we're going to invest all of our capital base in these two single assets. And as is the case with many problems in finance, the idea is that you would want to maximize your return while, and this is what we're interested in over here, minimizing our risk. So minimizing the risk, the uncertainty, the variability within the total expected return. Our total return is, of course, alpha X plus 1 minus alpha Y. And that variability is quantified through this function, which is known as the variance function. Now, it just so happens that you calculate the variance of the addition of two random variables. We don't actually go into that, so there isn't that step, in fact, so I'll skip it. But the value of alpha that minimizes this variance, so every value of alpha will give you a specific variance. You minimize that variance, you minimize the risk, the uncertainty within the total investment return. And this is just an example. What we're going to focus on today is bootstrapping. But we're doing it in the context of this scenario inspired by portfolio allocation theory. This value of alpha minimizes the variance. Now, the thing is that in practice, you don't know the variance, which is sigma y squared of y. Neither do you know the variance of X, which is sigma X squared, and neither do you know the covariance of X comma Y. And excuse me, and this is where bootstrap comes in. We're going to probably look at raw data and use the raw data to estimate these three quantities, and our estimates will be assigned sigma squared hat, sigma y squared hat, and sigma xy hat values. Once you have those values, you would calculate an estimate of alpha using the same formula as above. Now, we start by looking at the true, in fact, they're simulated. So they're simulated. So each panel has, doesn't look like 100, and that might be, you name it, maybe 50 observations. No, it is 100. Is 100 only these? Looks like less to my eyes. we're starting from quite an artificial position where you actually know the parameters. So what the authors have done over here is that using the actual parameters, using the variance of x and the mean of x, and using the variance of y and the mean of y, they've generated, oh, and also their covariance. Looks like we have a positive covariance over here. They've generated the data, and then they can, I guess they can calculate sigma x just by looking at the x components. Just by looking at the x components, and sigma y, as well as the covariance, and actually just calculate. I mean, in many ways, it's this formula, isn't it? It's with the hats. This is not bootstrapping. For the time being, this is just, I describe it as quite an artificial situation where you actually already know the values of sigma y, mu y. Mu y is the expectation. If you know those parameters, then you can generate this data. And we're going to do it 1,000 times. So for each of these panels, and you're going to have 1,000 of these panels, you can estimate alpha hat. And if you give them all the same kind of weighting or the same importance, you just say, okay, what is the mean of the alpha? And that would appear to be 60%. And in fact, we already know the true value. If you had to, like I said, this is, we're playing God over here. It's the exact reverse situation as that that we would have in practice. So how's the 0.6 being calculated? You're just substituting these three values in the formula, and you get 60%. So to minimize the uncertainty within this formula is suggesting a 60% allocation to asset X and a 40% allocation to asset Y. And then you calculate the standard deviation. It's this formula. You don't need to know it for the time being, at any rate. And this is the standard error of alpha hat. So you have the mean of all these alpha hats, and you also know the confidence interval. So if you think of it as the real line, this is your estimated alpha, the alpha bar. This 0.083 is giving you an idea of, I guess, the uncertainty within this alpha. In fact, you would get 60%, which is the true value, would be in this interval. If you add 0.083 to 0.59996, you would exceed 0.6. Now, in practice, and this is what we've been saying, however, the procedure for estimating the standard error of alpha hat outlined above cannot be applied because for real data, we cannot generate new samples from the original population. If you have a data set, if you've just looked at the asset performance over the past 30 days, and you have an observation for each day, then all you have is just a sample data set. You don't actually have the standard deviation or the expectation of those two variables. And this is where Bootstrap comes into the picture. However, the Bootstrap approach allows us to use a computer to emulate the process of obtaining new sample sets so that we can estimate the variability of alpha hat without generating additional samples, rather than repeatedly obtaining independent datasets from the population. We instead obtain distinct datasets by repeatedly sampling observations from the original dataset. And this is what we had 2 days ago when we last met. You have your, in this case, we're looking at two variables, x and y. And we're generating is each one referred to as a bootstrap? Yeah, a bootstrap data set. So over here, without replacement, so with replacement, excuse me. So when you select 3, you're not precluding the possibility of selecting it again. The sampling is performed with replacement, which means that the same observation can occur more than once. Can we see this in R? Last time I started typing, and it may have actually been correct. If you type sample, but for some reason when I tab, yeah, that looks, have I used sample? Did I accidentally, oh, because I took sample over here. Is it, let me just clear the environment. Okay. I'm just going to show you how to take these samples with the replacement within R. So let's say I have 1, 2, 3, 4, 5. Let's take a 6-sided die. Just these 6 values. What we can do with the sample function is you tell it you, for example, tell it to pick 4 values, replacement true, and probability. I think you can actually give you can sort of have it being without specifying the probability. I think they're all equally likely. And look, I generated 4, 1, 2, 4, and then I do it again, and then I do it again, and then I do it again. Let's pick all 6 of them, like what the book is doing. Let's pick all of them, like this. And maybe you want to do it 100 times, for example. So 1 to 100. So this. And if I run this, it doesn't actually display each one. Yeah, you probably have to save it as something. So for example, I don't know, randomized. And then we do return. And now we're going to get 100 That's interesting. If I asked it to return, why doesn't it? Anyway, the last one is 3, 5, 2, 3, 3, 5. All this just to show you how to do it in R, at least this initial part where for example the book from 1 to 3 has generated 3, 1, 3, 2, 3, 1, etc., etc. Right. We can use Z asterisk 1, so that's the first bootstrap dataset, to produce a new bootstrap estimate for alpha, which we call alpha hat asterisk 1. So using this bootstrap dataset, you now calculate alpha hat 1. How? Well, we have the formula from portfolio allocation theory. You just need delta x at sigma x squared, sigma y squared, and the covariance of x and y. Plug them into that formula, and you have your alpha. We'll do it so many times, b times. You have from alpha asterisk hat 1 until alpha asterisk hat b, and then you can compute the standard error using this formula. Right. Yeah, I think this is just standard definition. You are taking the mean. This is the mean, isn't it? It is, you add all the alpha asterisk hats from 1 to b, divide by how many there are, and then you calculate the standard deviation or the standard error by saying each alpha hat asterisk r, each one, how different is it to the mean? You square, this is just the definition, you square, then you always divide by 1 over b minus 1, and then square root everything. And then square root everything. I wonder if let's wait for the labs. I was going to tell you maybe we'd try doing it ourselves. I mean, we could do it here, surely. Trying to remember what we had typed. So we had x and y. We even had alpha hat. Yeah, I mean, we did quite a lot of work over here, didn't we? So let me just clear the environment. Had this and this. Then these were the alpha estimates. Then this, the standard deviation, and then this to get an idea of how large the standard deviation is. Yeah, I remember getting like 10% last time, and even today we have 0.09. So could we, what we'd first have to do is we'd have to create a data set. Can you do as data frame x comma y? That doesn't work. So that doesn't work. What about without the full stop? That doesn't work either. So could you maybe c-bind x comma y? Okay, so that looks a bit more promising. But would this be, if I had to save it as something, just call it my data? What kind of object is it? You can always ask our class my data. It's a matrix or an array. Can maybe now can we tell it as data frame and we give it my data? Okay, now that works. So now my data, if we do class my data, okay, it still tells you matrix array. So we have this data over here. You can even see it. Quite that text is quite small, but you can see it over here. And so we have 100. We have 100. I'd just like to show you how would you create like a new data set. I actually don't really know how because of the repetition. Or maybe I do know how. So if I do sample and I say from 1 to 100, it's just 100 rows, just 100 rows, just like the diagram had 3 rows. So my 100 is kind of like this 3 over there. And if I say size, I'm going to create a bootstrap data set. So with 100, the 100 matches the 100. And I say replacement true. And I do it. So our first row is going to be the 55th row, then the 32nd row, then the 83rd, but there is repetition, right? So for instance, I don't know if you're seeing any repeated rows, but I would be surprised if there isn't any repetition. So for example, the 32nd row is going to be repeated over here, and just maybe find one other repeated row. It's a fun game to play, isn't it? 857. Anyway, it's actually a miracle that I managed to find one of them. So there is repetition over here. There might not be repetition. They might all be distinct. After all, we're picking 100 from 100. But oh yeah, 13. The 13th row is repeated over here. And can we save it as vector? I don't know. New. I'll just call it new rows or something. And would it work if I say my data like this, new rows, comma. Okay, and that seems to have worked. So didn't we earlier say that the second row is like the 16th row? Let's see, the second row is, can we get done? Oh, but that hasn't worked, has it? The second row is this. And the 16th row is this. I wonder why this hasn't worked. So the second row was 1.27 originally. It has actually changed, hasn't it? But I was expecting the second row to be the 32nd row, 32nd, which is this. Anyway, we'll see in labs how to do it. What I was attempting over here was starting from this data set and getting a data set where you've jumbled them up and maybe there's repetition as well. Okay. Yeah, so this is how you'd calculate an estimate of the standard error of alpha hat. The bootstrap approach is illustrated in the center panel of figure 5.10, which displays a histogram of 1,000. So yeah, you do it 1,000 times, and from each bootstrap, you calculate the alpha. You get this distribution with this box plot, also known as a whisker plot. This span was constructed on the basis of a single data set and hence could be created using real data. That's the idea, right? The things that we're doing, we would like them to work on real data. Note that the histogram looks very similar to the left-hand panel, which displays the idealized histogram of the estimates of alpha obtained by generating 1,000 datasets from the true population. You know the true population if you know the parameters, the mean, the variance, if you know those statistics. In particular, the bootstrap estimate, standard error of alpha hat, is 0.087, very close to the estimate of 0.083, obtained using 1,000 simulated datasets. Okay, very good. Now, moving on to the lab, and why don't we share my screen, place these side by side, remove this, remove the menu bar, enlarge a little bit, and hopefully we'll get to a bit of this in R. So let's type, let's comment it out, 5.3 lab, and we're doing cross-validation. Until now, the shortest chapter, only around 50 pages. I'm reading a really interesting paper right now, produced by the Swiss Actuarial Association. And yes, Wuttrich, the same individual I mention every other session, is one of the authors, and they mention all these ideas: cross-validation, bootstrap, regression, classification. In this lab, we explore the resampling techniques covered in this chapter. Some of the commands in this lab may take a while to run on your computer. Okay. So the validation set approach. The validation set approach. So is this where we're doing cross-validation? Let's have a look. We explore the use of the validation set approach in order to estimate the test error rates that result from fitting various linear models on the auto dataset. And we had kind of done this, right, already without, and we were very happy with our results that time. Was it, I think it was this one, right? Where we regressed miles per gallon on horsepower. We used the quadratic regression, so it's actually horsepower and horsepower squared, and we had calculated the leave one out, cross-validation, mean square error. I'd just like to remind you what we're doing in cross-validation. The idea is that you would usually want to test your model by calculating the mean square error, and hopefully it's as you get it as low as possible on some kind of test data set. The test data set is data that you haven't used. Now usually you want to use all the data, because if you're saying, okay, I'm going to leave out 20% of the data, then your model as a result is probably going to be inferior because you've left 20% out. The reason why you're leaving it out is so that you can test the predictive power of the model, how well it predicts the response variable. And you would want to test that predictive power on observations that haven't been included in the design of the model. That's known as a holdout sample or an out-of-sample dataset. Now, in cross-validation, what you do is you actually, for example, in the leave one out method, and I'm sure you remember all these things, but we've made a lot of progress recently, and I'd still like us to remember what's going on. In the leave one out approach, you leave out the first observation, you perform the model fit on everything else, the blue, and then you use the parameters estimated based on the blue data to predict the response for the left out data, and you calculate the mean, you calculate the square error, right? So actual minus expected squared. It's a very, very standard approach that when you're calculating the difference between actual and expected, you subtract and you square. So this is probably going to be quite repetitive. It's nice to see how the authors do it. So let's have a look. Before we begin, we use the setSeed function in order to set the seed for R's random number generator so that the reader of this book, that's us, will obtain precisely the same results as those shown below. It is generally a good idea to set a random seed when performing an analysis such as cross-validation that contains an element of randomness so that the results obtained can be reproduced precisely at a later time. We begin by using the sample function. This is what we're using right now, right? To split the set of observations into two halves by selecting. Okay, so this is not cross-validation. This is just validation. Validation, you're just splitting the data, for example, into 50-50 portions. You use, what was I typing? Here we go. You use half the data to fit and the other half to calculate the test mean square error. And you want to reduce that mean square error. Okay, so let's see, library, ISLR. ISLR. Okay. And we're going to set our seed 1. What I'm not sure of is that when you set the seed, I know what it does, but does it only influence the first, the next line of code? So train, that sample command, we're going to have just says 392. So I don't need to say, I would have expected 1 until 392. And half of that, so 196. Why 392? Because we're going to work with the auto data set, data. And if you look at its structure, it is 392 observations. So we're going to only work with half for the fit, and then we'll use the other half for the test mean square error. Okay. So this gives you always want the same, right? Just for consistency. So we'll have this like that. Meaning. Oh, by the way, we didn't specify replacement, true or false. We didn't because the sample function, you will notice that the replace by default is false. So when the book writes sample 392,196, that means that you're just taking the first 392 positive integers, and you're going to take you're going to take a random sample. You're going to pick 196 of them at random. Okay. Meaning you're going to take the 324th observation, the 167th, etc. Here we use a shortcut in the sample command. C question mark sample for details. I guess the shortcut is that we're not writing x is equal to 1 is to 392. We then use the subset option in LM to fit a linear regression using only the observations corresponding to the training set. Okay. So LM fit, this is the name. Now we do LM. The formula is going to be miles per gallon on horsepower. The data is the auto data set. And subset, let me just tell it to train. So if you run this, and we do, for example, summary, ln fit, what do we get? We get these two parameters, your intercept parameter and your slope parameter. Okay. Now, last time we did it in kind of a quite an inefficient way. To calculate the expected, we wrote the formula. We explicitly wrote it. Intercept term, linear coefficient, quadratic coefficient as estimated over here. A much faster way is what the book is doing, and we have used this function before. And that should be the predict function. Here we go. We now use the predict function to estimate the response for all 392 observations. And we use the mean function to calculate the mean square error of the 196 observations in the validation set. Right. Okay. Okay. So now we're calculating the, I've been referring to it as the test mean square error. Strictly speaking, is the validation mean square error. But so this is on the data that we haven't used to fit. And we're going to specify that by saying negative train. So over here in the subset, we used the train for training. Now it's like we're going to take like the negation. So I wonder what we actually get if I just type negative train. Ah, okay. So in that context, it just turns every value into a negative value. But this is going to be different. If it's in the square brackets, it realizes that it means it's what you're going to take what isn't in the chain. Okay, so let's see. So we're going to attach the auto data set. And we're going to calculate predict. You need to tell it which parameters are you going to use from this linear model. So predict ln fit. And you're going to say auto. So that would be on all the auto observations. So for example, the 59th observation, we're predicting miles per gallon as a function of horsepower. We get 27.71. But we only want on the values that we did not include in the training data set. So if you do it like this now, what do you get? You get the 370 observation, but then 371, 372, 373, and 374, those were clearly in the training data set. If we go over here, can I find at least one of them? 37. So 375 was in the training data set. So over here, what you'll see, wait a minute. So why is 375 over here as well? It's odd. Not what I was expecting. Strange, isn't it? Is that I spotted 375, right? Didn't I, somewhere over here? Let's find another one. So for example, 299. Isn't 299 going to be excluded over here? Oh no, it isn't. So I actually think I have something wrong over here. I think um hmm. So our LM fit wasn't on the training, but aren't I now doing predict but exclude train? Hmm. That maybe, or maybe you need to put this in brackets like this. Hmm. No, right? Still, yeah. Okay. Let's see if at least we get the same value. So we're doing actual versus expected, the actual MPG, and it knows that it's from the auto data set because of attached. The predict. You calculate all this. You also square it. And then you take the mean of all these values. Yeah, in fact, we don't agree with the book. So there's getting something wrong over here. Ah. Hmm. That's irritating, isn't it? What might I have done? That's wrong. Let's run the whole thing again. Hmm. Yeah, something is definitely off because and it didn't look right, did it? Because the strain has these values. Let's sort them in ascending order. As for example, 1, 9, 13. But when I calculate this is 1, 9, 13. Okay, so it's clearly, oh no, this is 2, 3, 4, 5, 6, 7, 8. No, this is fine actually, isn't it? This is fine. but why don't we agree with the book? But yeah, the training is the 1 and then the 9th. So for example, over here, it's going to exclude the 389, the 390. No, okay, but why does it have 390 over here? And why does 390 appear over here as well? That's strange. Because it starts out fine. 1 is in the training, so 1 doesn't appear. Instead, these, the 9, 9, 13. That's really strange, isn't it? So for example, it excludes 383. And 383 is here. But then it does not exclude 384. And 384 is here. Hmm. Right. It's a bit disappointing. It doesn't look right, does it? Hmm. Just gonna have to move on. I don't know how to. It doesn't look right, and in fact, we're not getting their value. So they have 26.14. Anyway, therefore, the estimated test mean square error for the linear regression fit is 26.14. We can use the poly function to estimate the test error for the polynomial and cubic regressions. So it's 2 further linear models, but this time instead of on horsepower, on a quadratic function of horsepower and on a cubic function. In fact, the test mean square error drops to 19.82, and then it drops to 19.78. These error rates are 19.82 and 19.78 respectively. If we choose a different training set instead, then we will obtain somewhat different errors on the validation set. So you get 23.30, 18.90, and 19.26. Using this split of observations into a training set and a validation set, we can find that the validation set error rates for the models with linear quadratic and cubic terms are these 3. These results are consistent with our previous findings. A model that predicts MPG using a quadratic function of horsepower performs better than a model that involves only a linear function of horsepower, and there is little evidence in favor of a model that uses a cubic function of horsepower. Okay, so that was, unfortunately, we didn't get the exact numbers that they have, but at least hopefully we understand the principles. Although it would be nice if we got to the bottom of why this isn't working. And now we're going to move on to the leave one out cross validation. This can be automatically computed, so we don't need to write all that code that we wrote last time. for any generalized linear model using the GLM and the CVGLM functions. In the lab for chapter 4, we use the GLM function to perform logistic regression by passing in the family binomial argument. But if we use the GLM function to fit a model without passing in the family argument, then it performs linear regression just like the LM function. So for instance, GLM MPG on horsepower, given the auto dataset, will give us this intercept parameter and this slope parameter. And if you do the same thing, but with LM instead of GLM, you get the same parameters. So these yield identical linear regression models. In this lab, we will perform linear regression using the GLM function rather than the LM function, because the latter can be used together with CVGLM. The CVGLM function is part of the boot library, so we'll have to set up the boot library. So library boot. We're going to save everything in GLM fit. GLM MPG on horse power. Data is the auto dataset. And now we can create what we're going to label as the error, the CV error. And apparently it's this function, CVGLM. It also tells you from which package. If you see base or stat, those are typically bundled with vanilla R. And then you know, libraries are what make R so powerful. And we're using the boot library over here. And we're going to say auto GLM fit. Which gives us all this. But what we're interested in is where they are, those two. So let's see. This is why are there two of them? Or are they meant to be the same value? Not entirely sure. Remember, this is what we had done manually. We had actually told, specify to R, exclude the first observation, do the fit, actual versus expected. Exclude the second observation, do the fit, actual versus expected on the second observation. In this case, the numbers are identical up to 2 decimal places and correspond to the leave one out statistic given 5.1. Below we discuss a situation in which the two numbers differ. What are these two numbers? Our cross-validation estimate for the test error is approximately 24.23. We can repeat this procedure for increasingly complex polynomial fits. To automate the process, we use the for function to initiate a for loop which iteratively fits polynomial regressions for polynomials of order 1 to 5, computes the associated cross-validation error, and stores it in the ith element of the vector CV error. We begin by initializing the vector. So you initialize the vector. I usually take null. Sure we can find it. It's like a signature move before these for loops. They're taking just 0, they're just taking 5 zeros, repeat 0 5 times. And then for each loop in the ith entry, they swap out that 0 with the leave one out cross validation mean square error. It's these 5. We had got the 19.25 as well last time with the quadratic fit. And it's the same observation that from linear to quadratic, you see the significant decrease in the cross-validation mean square error, and then only marginal changes from the quadratic through the quintic fit. As in figure 5.4, you remember figure 5.4? It was this one. See a significant drop, and then there are hardly any differences. We must be somewhere over here, right? Okay. Okay, now K, fold cross validation, would be interesting if there's a, the CVGLM function can also be used to implement K fold, CV. Below we use K equals 10, a common choice for K on the auto dataset. So when K is 10, what are you doing? You leave out the first 10% of the data, fit, and do actual versus expected. Then you leave out the next 10% of the data and you repeat. Now, how do we do this? How do we do this? Because it's still the same command, isn't it? It is cv.glm, right? But now you specify, you say cv.glm. Not only do you say auto and glm fit, but you say k equals 10. So I wouldn't be surprised if when we type glm, yes, look, so the default k, if you don't specify a k, the default is just n, n being the number of observations. Whereas instead of partitioning into n partitions, you're going to partition into 10 over here, because you're saying k equals 10. Notice that the computation time is much shorter than the leave one out CV. I think there's a way in R you can actually tell it how long, you can put a line where it will output how long it took to run. Obviously it depends on the laptop that you on your hardware. We still see little evidence that using cubic or higher order polynomial terms, Okay, so now there's the bootstrap, and bootstrap's going to be maybe a bit more interesting because I think this is the first time we're going to use the portfolio data set, although actually, what's the structure of this portfolio data set? Okay, so it's just 2 variables. So we have 100 observations. Those are, I guess, well, we could ask what these are. Are they just the daily returns? A data frame 400 observations. Yeah. Okay. Well, maybe this is what they were using in that section where we're doing alpha. So if we do plot x comma y. Yeah. So I probably need to attach right first, otherwise you can't really blame. So these are your returns, and you have what looks like positive correlation. And I mean, yeah. So what we'll probably do is tomorrow we'll move on to chapter 6, linear model selection. So I would imagine selection is like which, if you have like a data set with 20 fields, 20 different characteristics, how many and which would you use?